All right, so we'll first do a problem on Hess's law. This is a thermodynamics problem. So delta H of a reaction, so delta H stands for enthalpy. Okay, and it means heat flow. So here in Hess's law, we have to do some manipulation. Okay, we have to do some manipulation. So here is the equation that we do not know the enthalpy for. We don't. But we do know the enthalpy for these two equations here. Okay, this one and this one. So what can we do with these two equations to get this? Okay, it's kind of like the same problem we did in class the other day, this type of problem. All right, we did this in class. We're going to have to either flip a reaction, we may have to multiply a reaction, we have to do something, okay, to these two to get this. So first thing I would do is I would look at my reactants. Okay, I have an H2S, but I have two of them. And where's it at? Is it at the reactant side or the product side? Reactant side. And if you look here, where do I have the H2S? Product side. And not only that, here in my net, I have two. So what do I need to do here? I not only need to flip this to get it on the reactant side, but what else do I need to multiply it by? Yeah. So let's flip the second reaction. Ultimately, we want to get to this. So let's flip second reaction and multiply by 2. Okay. Is it okay if I do it all in one step? Okay? Yes. Okay, I like that. So I flip it, and what will that do to the sign? Positive. And if I multiply by 2 to get 2H2S, what will that do to this? Double or multiply it by 2, so that's going to be...
that would be 69.6.
69.6. All right, very good. All right, so 2H2S plus 2H2O. Okay, that's going to go to SO2. So multiply by 2, right? 2H2S, that means 4H2O, 2SO2, and 6H2. Okay, 6H2. Is that right? So flip it, multiply by 2, 2H2O, 4H2O, 2SO2. Yeah, okay. And the delta H of the reaction is going to be, what would you guys say, 69.6? That's 69.6 kilojoules per mole. All right, so what's next here? So that's done. All right, I need an H2 here. Okay, so what should I do to this equation? I need 3 oxygens, and I need SO2. I need 2 SO2, but I got 2 SO2. So what should I do with the first one? I got an H2 here. I think what I'm going to do is I'm going to multiply this one by what number?
6.
Okay, 6. I think you guys see it. And then add it to which one? To this one, okay. Multiply first reaction by 6. And add to previous one. So multiplying this by 6, I'm going to get 6H2, okay, plus 6 halves. What's 6 halves?
3.
Good, 3. multiply 6H2O. Okay, what's minus 241.8 times 6? Can you do that in your head?
Give me a second. So it will be 1,450.8, right?
1,450.8. Let me try it on my calculator. 1,400
50.8.
negative.
Yes.
Negative 1,450.
50.8.
What is it again? I'm sorry.
Negative 1450.8.
Okay. All right, so multiplying this by 6, we get negative 1,450.8. Okay. All right, so let's add these up together here. All right, do you guys see what cancels out? Okay, those cancel out. And then the 4H2O cancels out with the 6H2O, leaving how many left over? 2. And this is the 2H2O that we see there in the product side. And then the 2SO2 is here. And then we have the 3O2 is here. I think we're good. Okay. So our net is 2H2S gas plus 3O2 gas. It's going to go to 2SO2 plus 2H2O gas. Okay. So if you add two reactions, what do you do to the enthalpies? You also add them, right? So what's 69.6 minus 1450.8 minus 1,381.2? Is that what I'm getting? Okay, so this will be my answer. Right, so would this be an exothermic reaction or an endothermic reaction? Okay, the negative sign tells us that this would be exothermic, which would mean that it would also give off heat. Okay, so something like this on the exam, a different reaction, but you're going to do pretty much the same thing. Okay, same type of problem on the exam. Okay, so you're going to follow the same pipeline. Right. This is a Chapter 7 question when we were talking about electron configuration and quanta. So what is the wavelength and energy of blue light? So blue light can be a wave. Okay, can be a particle. Okay, that particle is called a photon. Okay. So the equations that you will need to solve for this one, I'll give you them on the exam, is you need the energy, which is H times V. This H is Planck's constant, which is 6.63 times 10 to the minus, I think it's 34, joules times second. Okay, this is H, Planck's constant. E is energy, V is frequency. Another equation we need is that most of these travel at the speed of light, so lambda times V. And here the speed of light is 3.00 times 10 to the 8 meters per second. Okay, speed of light. So wavelength and energy. Okay, so we have here the wavelength. Let's figure out the frequency and then plug it in here to get the energy. So that's how I'm going to do this problem. So 453 nanometers. 1 times 10 to the minus 9 nanometers. No, 1 times 10 to the minus 9 meters is 1 nanometers. So nano is 10 to the minus 9. Yeah. So 1 nanometer is 1 times 10 to the minus 9 meters. So what's 453 times 10 to the minus 9? Okay, it's going to be 4.53 times 10 to the minus 7 meters. Okay, I think I can do that in my head. Yep, 4.53 times 10 to the minus 7 meters. So this is going to be our wavelength lambda that we want to plug in here. So we're going to convert the nanometers to meters. 1 nanometer is 1 times 10 to the minus 9 meters. And doing that for this wavelength gives us a wavelength in meters of 4.5 times 10 to the minus 7. So that's our wavelength. We'll put it in this equation. Okay, c is the speed of light, which is 3 times 10 to the 8 meters over second. I'll give you all these equations. Okay, divided by lambda, which is 4.53 times 10 to the minus 7. Okay, that's going to equal to frequency. Right, so the frequency V is the meters cancel. And what's 3 times 10 to the 8 divided by 4.53 times 10 to the minus 7? Uh, 6.62 times 10 to the 14 hertz. Okay, hertz. So that is the frequency in hertz, and then let's plug that in here. To get us our energy. Okay, so we'll multiply this frequency by Planck's constant, which is 6.63 times 10 to the minus 34. Right, and that should give us the answer. Right. So E is equal to HV. .63 times 10 to the minus 34 joules times second times 6.62 times 10 to the 14 hertz. Okay, 1 hertz is inverse seconds. Seconds, because remember, hertz is equal to 1 over seconds. And what do we get when we do that? So 6.62 times 10 to the 14th times Planck's constant. Uh, 4.39 times 10 to the minus 19 joules. 4.39 times 10 to the minus 19 joules. So this is the answer. So similar type of problem on the exam. Okay, I'll give you the equations and the constants so you do not have to memorize them. All right, let's do about 2 more problems and then we can finish this up on Tuesday. All right, a piece of iron of mass 150 grams has a heat capacity C of 25.1 joules over moles degree C. How much heat is required to raise the temperature of iron from 35 to 85 degrees? Okay, so we have a big block of iron here. 155 grams of iron. Okay, we're going to heat it. Okay, it's originally at 35 degrees C. We're going to heat it to 85 degrees C. And we want to know how much heat do we need to get that to from 35 to 85. All right, so the equation here is Q equals mc delta T. Q is heat, m is mass, C is the heat capacity, and then delta T is final minus initial. Okay, delta is always final minus initial. Okay, so we got our mass here of 150 grams of iron. Okay, C is 25.1 joules over mole Kelvin over mole degree C. And then we need to convert this to moles because grams and moles don't cancel. So for every 1 mole of iron, this is iron, right? Iron. How many grams are in 1 mole of iron? 55.85 grams. Okay, so we have our mass. We have C. We converted it to cancel out the moles. And then delta T final, 85 degrees C minus initial, 35 degrees C. So this is what I'm getting to solve this problem. Okay, mass. C, I just had to convert it to cancel out the moles, and grams. The degree C and the degree C cancel, and I am left with joules, okay? Joules, which is energy. Heat is in the units of energy. All right, so something like this on the exam. Let's go ahead and do this. 85 minus 35 is 50, right? So 50 times 25.1 times 150. Okay, divided by 55.85. And I'm getting 3,371 joules. Okay? What does the positive sign tell you? Does that mean you have to add the heat? Yes. Okay. Why do you have to add the heat? Okay, you need to add heat to raise the temperature from 35 to 85. So, yeah. Okay. So these 3 problems are similar to the type you'll see on the exam. All right, let's fill out this table before we end class for the day. Okay, so there's different types of heat, energies. Okay, there's many different types of energies. But overall, the energy can do work, or it can be lost as heat, okay, or taken in as heat. Okay, so the total internal energy is Q plus W. So in the internal energy of the system, we have Q contributes, work contributes, okay? Within that system, it can take in heat from the surroundings. It can give off heat Q to the surroundings. It can do work on the surroundings, or surroundings can do work on the system, which is the main chemical reaction. So we're going to fill this out here. So the work done on the system by the surroundings, on the system. So what would be the sign of the system? Work done on the system by who? So who does the work? What sign does that get? Okay, that will get the negative sign. Okay, and if this gets the negative sign, what will the system get? Positive. Okay, what about a differing situation, the opposite? Work done on the surroundings. On the surroundings by who? So who does the work? System. They get negative, and the surroundings is going to take that work and be positive. So it's the same value, same number, but different sign. All right, how about if the energy is released to the surroundings? Okay, what will the delta H be? Energy is released to the surroundings. Okay, we call that an exothermic reaction. Okay? And if the surroundings take that heat energy, what will its sign be? Positive. Okay, so relative to the system, this is exothermic. The reaction would be exothermic. What happens if the surroundings intake heat, so from within or from in? Heat goes into the system. Positive. Okay? And who gives the heat to the system? Surroundings, so that would be negative. We have 3 more minutes. Let me do this one quick problem because it will be really quick. Okay, let's do the last one here. Okay, and then we'll fill up this electron configurations and do some touch-ups on Tuesday before your exam. Okay, if the system absorbs 25 kilojoules of heat from the surroundings, heat, that's going to be Q, from the surrounding, it absorbs it. Will that be positive or negative? Absorbs is positive, very good. Okay, and does 35 kilojoules of work on its surroundings? Does 35 kilojoules, is that positive or negative?
Negative.
Good, negative. Okay, this is work. W. So what would be the change in energy of the system? Negative 10 kilojoules. So in the end, it is doing, the net energy of the system means it's doing work on the surroundings, okay? Because it's negative. You can say exothermic. The negative sign tells us that. So we went over those types of problems, very similar to the exam. We'll wrap it up on Tuesday as well. And And then Thursday is your exam.